Good morning, everyone, and welcome to this lecture. This is lecture number 2, and we are going to discuss magnetic effect of current. Now, what is this magnetic effect of current? In the last class, we had seen what is magnetic field, what is magnetic flux. A magnet creates magnetic field. Do we remember this? Do we remember what we had discussed in the last class?
Yes, sir.
Okay. Now, we can move ahead and see how a current produces the same effect as a magnet, that is known as magnetic effect of current. It was discovered in the year 1820 by a scientist of the name of Oersted, and this is known as the Oersted discovery or the Oersted experiment. And what did he discover in the Oersted experiment? If you have a current carrying wire, and you bring a compass close to that current carrying wire. Now, what is a compass? Do you know what is a compass?
Yes, sir.
What is a compass?
An instrument which is used to find the direction, something like that.
Find the direction of what?
North and South Pole.
It is an instrument which is nothing but a magnet, and it can detect magnetic field if they are present anywhere. If there are no magnetic field present, this compass will always point in the direction of north-south, because your Earth also behaves like a magnet. So if there is a compass, that will always deflect if there is a magnetic field. Now, what experiment Oersted did? He had a current carrying wire. As you can see, this is a wire carrying current. When a compass is brought near a current carrying wire, it shows deflection. When a compass is brought near a current carrying wire, when a compass is brought near a current carrying wire, it deflects. What do you mean by it deflecting? It deflects. What does that mean? Showing the presence of what?
Magnetic field.
Showing the presence of magnetic field B. That means that a current carrying wire can produce a magnetic field. He also found out that when the direction of current is reversed, when the direction of current is reversed, then the deflection also reverses. That means the direction of this magnetic field is determined by the direction of current. When the compass is brought near, the deflection increases, and vice versa. So, this experiment tells us that a current carrying wire produces a magnetic field. This experiment came to be known as the Orsted experiment. When the current in the wire was increased, the deflection in the compass increases. This also tells us this current carrying wire, the field that this current carrying wire produces is directly proportional to the current. If the current is increased, the deflection increases. This is known as the Orsted experiment. I'll give you 2 minutes to note this down. So now we can understand and we can write all these points together. A magnet which is at rest produces a magnetic field. We have just seen it. A magnet at rest produces magnetic field, while electric charge at rest produces an electric field around it. That was electrostatics. And we have seen a magnet at rest produces magnetic field. Now, when we talk about a current carrying wire carries current. What do you mean by current? How is current produced? Yes?
By the movement of charges.
Are the charge moving with uniform velocity, or the charge is moving with acceleration, or are the charges accelerated? When current is flowing through a wire or a conductor, are the charges moving with
Charges are accelerated.
charges are accelerated? What is the acceleration of the charge? How much is the acceleration of the charge?
It
In a
is
current carrying
directly
wire, what is
proportional
the acceleration of
to
the charge? Yes,
potential difference.
charges are accelerated. Well done. And it is directly proportional to the potential difference. Anyways, when current is flowing in a wire, charges are not accelerated. They are moving with a velocity. If you remember, two classes back, we had seen that velocity. That velocity is known as,
Drift velocity.
so the charges are not accelerated. They are moving with a velocity which are known as drift velocity. It is very less, no matter so less. Charges moving with uniform velocity, which is the case of a current flowing in a current carrying wire. This charge is moving with uniform velocity. Is a current carrying wire. In a current carrying wire, charges are moving with uniform velocity, and that creates a magnetic field, and they do not create an electric field. But you have a charge which is moving with a uniform velocity, it will create electric as well as magnetic field. That means if I have a charge plus q moving with a velocity v, it will create both magnetic field and electric field. But when these charges are moving together in a conductor which carries current, this current carrying wire only produces a magnetic field and it does not produce an electric field. Do not write it. I will give you time to write it. First listen and try to understand. To produce an electrostatic field, remember, to produce an electrostatic field, you need a charge. But to create a magnetic field, you may not need a charge. You can create it by a magnet. You can create it by a current carrying wire as well. Now, when a current carrying wire or a current carrying coil creates magnetic field, and we have seen that we can find out the magnetic moment of that current carrying coil. What was the magnetic moment of a current carrying coil? Do we remember?
NIA, sir.
NIA. So it creates a magnetic moment. You can assume it to be behaving as a magnet or a magnetic dipole, but it actually does not produce as magnetic pole, but it behaves like a magnet it gives the illusion of a magnetic pole. So it can create a north and a south pole. Now, if we have a charge which is accelerating, my dear friend, it produces, apart from electrostatic and magnetic field, it also produces EM waves. Electromagnetic waves are produced by an accelerated charge. That will be the last chapter in this topic, EM waves, electromagnetic waves. So electromagnetic waves are nothing but what? They are produced by charges which are accelerated. So if a charge Q is having an acceleration, it produces magnetic field, it produces electric field, and it produces EM waves. So this is how we can put all these things together that we have studied till now. Electrostatic field is created by a static or a charge at rest. Magnetic field can be created by a magnet. It can be created by a current carrying wire. It can also be created by a charge which is moving with a uniform velocity. It can also be created by charge which is accelerating. To create EM waves, we need a charge which is accelerating. This is how all these types of fields and waves are created. Now I'll give you 1 minute to note down what we have done. Frame dependence of magnetic field. Now, as you can see, there is a charge Q. Let us say with respect to Earth, it is at rest. This observer O1 is also at rest with respect to Earth. O1 observer is looking at the charge. What will he see? What is this charge creating?
Electric field.
Electrostatic field would be a better way to say. For O1, the charge only creates electrostatic field. Why I am not using the term electric field? We'll come to know maybe 4 or 5 classes from now. We might forget it, that's a different issue, but we'll come to know the difference between electric field and electrostatic field. So the charge O1, no, the observer O1 will only see electrostatic field created. What will this person see? He is moving with a velocity v1 with respect to Earth. He is also observing the same charge q. What will he see?
Same electrostatic field.
He will see electrostatic as well as magnetic field, because in his frame of reference, the charge is not stationary. The charge is moving backwards with a velocity v1. So this observer O2 will see both the electrostatic field and the magnetic field. Let me call that magnetic field as B2. Coming to observer 3. Observer 3 is moving with a different velocity. What will he see? He will see the same electrostatic field, but he will see a different magnetic field, because for him, this particle is moving with a different velocity in its frame of reference. That means magnetic field depends on the frame of reference. Depending on from where you are watching this charge, the magnetic field may keep on changing. Magnetic field depends on the frame of reference. So what it means basically is magnetic field produced by a moving by a charge q depends on the reference frame. Do we understand this?
Yes, sir.
A charge, whether it produces an electrostatic or magnetic field, it is going to produce electrostatic field in all the cases. Whether you see a magnetic field or not, it depends on your frame of reference. Do we understand this?
Yes, sir.
Now, if I change the case and instead of a moving charge, I have a current carrying wire. If I have a current carrying wire, now remember, a current carrying wire only produces magnetic field. It does not produce electrostatic field. Forget about the electrostatic field. And this question can come as a question in your JEE. Current carrying wire, and I have an observer. And just to complicate things, let us assume that he is moving with a drift velocity Vd. Drift velocity Vd is the velocity with which the electrons in the conductor are moving. So now if he is moving with the same velocity Vd in the same direction as electron, which is opposite to the direction of current, what will he see? Will he see a magnetic field or not? Well, electrons will be at rest, but the positive charges and the conductor has equal number of negative and equal number of positive charges. Even though he is moving with a velocity which is equal to the drift velocity of the electrons in the same direction as the electrons, the positive charges will be moving in the opposite direction with respect to him. Yes or no?
Yes, sir.
And therefore he will see magnetic field, the same magnetic field, no matter how it moves. That means magnetic field created by a current carrying wire does not depend on the reference frame. Magnetic field due to a wire does not depend on reference frame. Do we understand this?
Yes, sir.
Because in a wire, there are negative as well as positive charges. If it was only one charge, then it would depend on the reference frame. We understand this?
Yes.
I'll give you 1 minute to note this down. You don't have to note down everything. You just have to note down the statement and you should be able to understand it from there. A magnet also produces magnetic field. We've already seen the magnetic field produced by a magnet, a bar magnet, magnetic dipole. We have seen its formula. In that formula, you never see the velocity coming anywhere. That means the magnetic field produced by a magnet does not depend on your reference frame. It does not depend on your velocity. Whatever velocity you are moving on the surface of Earth, Earth is creating a magnetic field. Does not depend on your reference frame. So, magnetic field created by a magnet does not depend on the reference frame. Only one case depends on the reference frame. And what is that case? That case is the magnetic field created by a single charge. It depends on the reference frame. Magnetic field created by a wire or a magnet does not depend on the reference frame. I'll give you a minute to note this down. And we come to this factor, and this term is going to come many times in the beginning, which is the current carrying element. What is a current carrying element? Current carrying element is nothing but a small length of the wire which carries a current. You can see this small length of the wire dl carries a current, and the direction of current is like this. This current carrying element is taken as a vector quantity, and the value of this current carrying element is I into dl. It's a vector quantity. The direction of this current carrying element is same as the direction of current. Do you understand this?
Yes, sir.
Note it down. What is a current carrying element? And the next heading is Biot Savart law, and it tells us how much is the magnetic field produced by a small current carrying element or current carrying wire. Here we have a small current carrying wire of length dl. Do you see this?
Yes, sir.
And we have a point P where you are supposed to find out the magnetic field. Since this current carrying element is very small, this will create a very small magnetic field. Let me call that magnetic field as dB. Now, what all factors do you think this magnetic field created by this current carrying element will depend on? We have already seen it in the Orsted experiment. You can apply some logic and tell me on what all factors this magnetic field dB produced by this current carrying element depend on.
Direction of the current.
Talking about the magnitude of field, not the direction of field. Let us first talk about the magnitude, then we'll discuss the direction.
Distance.
Okay, and
Amount of current flowing in the wire.
so it will depend on the magnitude of current which is flowing in the wire. It will also depend on the length of this current carrying element. If the length is small, the magnetic field is small. If the length is more, the magnetic field will be more. So basically, it will depend on the multiplication of I and dl. The multiplication of I and dl gives us the value of that current carrying element. It has been found out that it varies inversely with the square of the distance between the current carrying element and the point. If I make the distance twice, the magnetic field becomes 1 by 4. One more factor it depends on. It depends on this angle. Angle between what? Angle between what?
Current carrying element and that direction. Distance. R bar.
So it depends on the current carrying element dl and r vector, the angle between the current carrying element and r vector theta is the angle between dl vector or the current carrying element vector and r vector. R vector is drawn from the element to the point. If I put all of these things together, I will get the formula of magnetic field dB, the small magnetic field produced by the small current carrying element. One constant comes and no surprises. The constant is mu naught by 4 pi I dl sine theta divided by r square. Remember, it depends on theta. If theta is 0, that means the point lies ahead on the wire. Or if theta is 180, the point lies behind the wire, on the wire. The magnetic field is 0. This becomes the formula of magnetic field created by a current carrying element. The formula of magnetic field created by a current carrying element. What is mu naught?
Permeability, sir.
permeability of free space or vacuum, and what is the value of mu naught? We know this, right?
Yes, sir.
Now, what type of quantity is magnetic field? Is it a scalar quantity or is it a vector quantity? Magnetic field, is it a scalar quantity or is it a vector quantity?
Scalar quantities.
Magnetic field is a scalar quantity. Well done. That means electric field will also be a scalar quantity. Whenever we use the word field, it is always a vector quantity. Magnetic field is a vector quantity. So, if you are hearing for it for the first time, please remember it. Magnetic field is a vector quantity. Now, this formula that we have devised, what is it telling you? Is it telling you the magnitude? Is it telling you the direction? Or is it telling you both? What are you going to get from this formula? Magnitude, direction, both.
Both.
Both. Well done. We are going to only get the magnitude from here. I don't think how are you going to get the direction from this formula. No formula, if it's given in this form, can give you direction. This will only give you the magnitude of magnetic field. This will only give you the magnitude of magnetic field. It will not give you the direction of magnetic field. If there is a scalar formula of magnetic field, but magnetic field, as we have now known that it is a vector quantity, there must be a vector formula of magnetic field. And how does the vector formula of magnetic field look like? The vector formula of magnetic field looks like this. dB now becomes dB vector mu naught by 4 pi. There must be a vector equation here. So the vector equation looks like this. I dl cross r vector divided by r vector का magnitude cubed. The formula on the top will only give you the magnitude, but the formula here at the bottom of the ocean will give you both, because it is a vector formula. Everything is written in the vector form. We may not be using this formula, but we should know this formula. This formula gives us both the magnitude as well as the direction, because it is a vector formula. This formula will give you both magnitude as well as direction. We are not going to use this formula though. We are going to use the upper wala formula, the above one, the scalar one. If we are going to use the formula for scalar one, we need some way of finding out the direction of magnetic field. How will I get the direction of magnetic field? The direction of magnetic field will be given by
Right hand thumb rule.
by the cross product of dl with r. The direction of magnetic field will be given by the cross product of dl and r. And how do you find the direction of cross product? How do you find the direction of cross product? We find it by the right hand thumb rule or right hand screw rule or Maxwell screw rule or Fleming's right hand rule, whatever you call it. That is how you find out the direction of magnetic field. dl cross r gives us the direction of magnetic field. Whether you call it by any name, that does not change its significance. Right hand thumb rule. What does the right hand thumb rule state? If you want to find out the direction of cross product of two vectors, you use your right hand thumb rule. Right hand thumb rule. So, how do you find the direction of magnetic field? dl is your first vector. Cross r is your second vector. That must give you the direction of magnetic field. The thumb of your right hand should point in the direction of DL, thumb. The palm of your right hand should go in the direction of in the direction of the point, which point you are supposed to find the magnetic field. So your palm will go in the direction of R vector. This will go in the direction of DL or current. Your palm will go in the direction of R, and when you turn your fingers by 90 degrees, and you cannot turn them that way, you can only turn them this way. When you turn your fingers by 90 degrees, these three vectors are perpendicular. The direction of this fingers will give you the direction of magnetic field. That is how you find out the direction of magnetic field using the right hand thumb rule. Do we understand this? Right hand thumb or right hand palm rule. Do we understand this?
Yes.
I'll give you 2 minutes to note this down. And you must remember one more thing about this cross product. Cross product of two vectors is always perpendicular to the two vectors. That means this magnetic field B is perpendicular to both DL and R vector, or it is perpendicular to the plane containing DL and R vector. This is a special thing that you must remember about the cross product. The cross product of any two vectors is perpendicular to the two vectors that we are talking about. So if DL and R both lie in the XY plane, if DL and R both lie in the XY plane, in which plane will magnetic field point? If DL and R lie in the XY plane, in which direction will the magnetic field go?
Either Z minus Z or plus Z.
Either minus Z or plus Z, depending on how they are. Remember this? Just to give you an example of a magnetic field created by a long wire, how can we find out the direction of magnetic field? If this is your long wire, it carries current like this, it's given in your book, current like this. So I place my thumb pointing in the direction of current. I hope you can see this. If I have to find the field at this point, which is given in your book, so how are you going to find it? DL is here, point is here, so I point my fingers in that direction, and then I turn. You can see the magnetic field will be coming out towards me. Do we understand this?
Yes, sir.
Similarly, if you have to find out the magnetic field at this point, remember current is like this. So I put my thumb like this, I stretch my palm like this, and I turn. In that case, magnetic field will go inside. Do we understand this?
Yes.
Simply speaking, if your current carrying wire is like this, carrying current here like this, at point A, which is here, where will be the direction of magnetic field?
Into the page.
Into the plane, that means cross. On this side, what will be the direction of magnetic field?
Out of the page.
At point B, it will be outside of the page. If I want to find out at this point, it will be going like this. Do we understand this?
Yes, sir.
At any point, so basically you can see it is going to move in a
circular path.
Because it has to be in a closed loop. Do we understand this? Or this has gone above our head saying bye bye?
Understood, sir.
So the magnetic field would be like this. Do we understand this?
Yes, sir.
Yes or no?
Understood, sir.
Now, if you look at the same thing from a different point of view, from a different place, right now I'm looking it from the front. Current is like this. If I look at the same thing from the top, do we understand? Same thing from the top.
Yes, sir.
The same thing from the top would look like this. And I hope you can understand it. This is the same thing from the top. I mean, the direction are reverse. This case A corresponds to this case A. Do we understand this?
Yes, sir.
Current is coming towards you. And this case B corresponds to that case. They are written in just the opposite order. Do we understand this?
Yes, sir.
Anything coming towards you is cross, is dot. Anything going away from you is dot. So if it is dot, the field will go anti-clockwise. Do we understand this?
Yes, sir.
I am making anti-clockwise. For you, it will be looking clockwise, but I am trying to make anti-clockwise because you are on the other side of the screen. Are you getting my point, or it is going above your head, saying bye-bye?
Understood, sir.
Everyone got this? Yes or no?
Yes, sir.
Okay. Now, the diagram which is given here is actually given in terms of, now I reverse the diagram. Now, instead of current coming out, if I make the current flow in the clockwise direction, so now you can use the right hand cock rule. You can turn your fingers in the direction of current, and you can see, if you turn your fingers in the direction of current, magnetic field will go inside. Do we see this?
Yes, sir.
If the current is moving anti-clockwise, the magnetic field will come out. So it's the reverse of that entire thing. If the current carrying wire is like this, wee, magnetic field is like this, wee. If the current is like this, the magnetic field is like this. Do you understand what I'm saying?
Yes, sir.
Or it has gone above or it's saying bye bye?
Understood, sir.
Bye bye. Give you 2 minutes to write anything if you want to do. And you can note these three different forms of the Biot Savart law. How you can write magnetic field. This form we have already discussed. Yes or no? Instead of writing magnetic field like this, I could have written it like this. dB is mu naught I dl cross unit vector r divided by 4 pi into r square. Do we understand this?
Yes, sir.
This could have been written in this way. This, remember, is the vector form of the equation. The scalar form of the equation remains the same, mu naught by 4 pi I dl sine theta divided by r square. Do we understand this?
Yes.
The same equation is written in the form of current density. Do you remember what is current density?
Yes.
You can write this in this form also. dB vector will be mu naught by 4 pi j vector cross r unit vector divided by r square. Do you understand this?
Yes.
If I want to write this in the form of scalar, you can write a j sine theta by r square. Do you understand this? That form we don't use, so that's why I'm not realizing it. The most important form here is this one, which you might miss. This is the vector form of electric field produced by a charge moving with a velocity. Remember, whenever we have a vector form and it includes charge, this charge must be put with sign. You understand the meaning of sign?
Yes, sir.
If it is a positive charge, you must put positive. If it is a negative charge, you must put negative. We get this?
Yes, sir.
So this formula has to use charge with sign. You can also write this formula as dB vector will be equal to mu naught by 4 pi q v cross unit vector r divided by r square. Now the scalar form of this would look like this. dB will be equal to mu naught by 4 pi q v sine theta divided by r square. Well, what is this theta? What is this theta?
Theta is the angle between velocity vector and r bar.
It will be the angle between velocity vector and r vector. This will give you the magnitude of magnetic field. How will you get the direction of magnetic field? How will you get the direction of magnetic field? How will you get the direction of magnetic field?
Sir, if it is positive charge, we'll put our thumb in the direction of velocity.
Direction will be given by right hand thumb rule. You have to find the direction of cross product of V with R. But remember, it will only give the direction of magnetic field created by a positive charge. There is no way to find out the direction of field created by negative charge. So what do? Once you get the field created by the positive charge, if the charge is negative, just reverse it. Do you understand this?
Yes, sir.
So now I'll give you 2 minutes to note this down. So now if I give you a question where you have an electron E revolving in a circle of radius r, what will be the magnetic field created by this electron at the center of the circle? What would be the answer for this one? I'll give you a minute to tell me the answer. This electron is moving with a velocity v. I forgot to tell you that. This electron is moving with a velocity v. So how are we supposed to find it? This is the center O. The magnetic field B, or let me call it as dB, produced by this one will be mu naught by 4 pi. Charge is E, velocity is V. The angle between the velocity vector and radius vector, or the distance, is how much?
90 and r, sir.
90 and r. That is the magnitude of the magnetic field. What is the direction of magnetic field? So velocity is here, point is here, it is going outside, but that is the field created by a positive charge. This is a negative charge, so the field would be going inside. Do we understand this?
Yes.
Now instead of this giving this v, I could have given omega, so it becomes v is equal to omega r. So in terms of omega, the formula looks like this: mu naught e omega by 4 pi r. Do we understand this?
Yes, sir.
Now remember, omega is 2 pi f or it is 2 pi by t. So you can write the formula in various forms if you have understood this one. Do we get this? Oh, this has gone above our head saying bye bye.
Understood, sir.
Pakka, sir? You understand it, sir? Write down the formulae once and let me know once you are done. And we can use this Biot Savart law for a small element, and we can find out the magnetic field due to a straight wire. We are not going to get into the derivation of that thing. Derivation is not required, but we have to just see how does the formula look like, and this is the standard way in which you have to convert the straight wire. So what you know about the straight wire, you know the current I flowing in the straight wire. Do you understand this?
Yes, sir.
You know the distance r of this point A from the straight wire. You got this? So I is known, r is known. The other two things is that should be known is the length of the wire. Normally the length of the wire is not given. Instead of the length of the wire, we know this angle theta 1 and theta 2. If you know theta 1 and theta 2, you can find out the length of the wire. Or if you know the length of the wire, you can convert it in the form of theta 1 and theta 2. Do we understand this?
Yes, sir.
If everything of this nature is known, then you don't have to do anything but apply the formula of the straight wire and get your result and stay happy. And the result, do you know what is the magnetic field due to a straight wire? It is mu naught I by 4 pi r into sine of theta 1 plus sine of theta 2. This is the formula that you will have to use, but this only gives you the magnitude of magnetic field. How do you find out the direction of magnetic field? How do you find out the direction of magnetic field? Yes,
Using right hand rule.
using right hand thumb rule, you can find out the direction of magnetic field. No prizes for guessing this. If the point is on the right and the current is going up, the magnetic field will be going inside. If the point is on the left, magnetic field will be coming outside. Yes or no?
Yes, sir.
Looking at this point C and this point D, what will be the magnetic field at point C or D?
Zero, sir.
Why it is zero?
Like it is in the direction sine theta is equals to 0.
The sine theta is equal to 0, or it may be equal to 180 degree depending on how you are looking at it. Do we get this?
Yes.
Now instead of this wire like this, you can have a wire that starts from some point ahead of it. Do we get this?
Yes.
Now in that case, what will be the direction of magnetic field? What will be the magnitude and what will be the direction? Instead of the formula looking like this, the formula would start to look like this. Do we understand this?
Yes, sir.
Everyone gets this?
Yes, sir.
I'll give you 2 minutes to note this down. Now if I have a special case and I have an infinite wire, when I say infinite wire, it extends to infinity in one direction, it also extends to infinity in the other direction. What will be the magnetic field?
Mu naught I by 2 pi r.
So in that case, your theta 1 will be equal to theta 2 will be equal to 90 degrees, yes or no?
Yes.
So the formula will become mu naught I by 2 pi r. Do we understand this?
Yes, sir.
Now we can have one case where it is, I call it semi-infinite wire. When I say semi-infinite wire, the semi-infinite wire starts to look like this. In one end, it is going to infinity. In the other end, it is having an end, and you are finding the magnetic field at the end. In that case, what will be the answer?
Mu naught I by 4 pi r.
In this case, one angle theta 1 is 90. the other angle theta 2 is 0, doesn't matter which is theta 1 and theta 2, the magnetic field becomes mu naught I by 2 pi r. Do we understand this?
Yes.
You can also have one case
Sir, mu
where
naught
it
I by
may,
4 pi r, sir.
sorry, mu naught I by 4 pi r. You can also have one case where this point P is here. In this case, it is infinity. Distance is r. And this angle is given as, let us say, phi. In that case, what is the answer? Mu naught I by 4 pi r multiplied by 1 plus sine phi. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Special cases. The same thing I illustrated here. If both the angles are same, phi and phi, it becomes, the formula becomes like this. This is the case of infinite wire. This is the case of semi-infinite wire. Do we understand this?
Yes, sir.
Do you want to note it down? Note it
Yes.
down fast. And this is the question. There are two infinite wires, one carrying current 2I in the upward direction, one carrying current I in the downward direction. There are some points given, A, C, and D. B is not given because B is for magnetic field. You have to find out the magnetic field at point A, C, and D. And you also need to find out where the magnetic field might be 0. Where will the magnetic field be 0? Will it be 0 in between? Will it be 0 on either side? I give you time to think about it. So, how are we supposed to find out? Let me call this wire as the pink wire carrying current like this. Let me call this as the green wire carrying current like this. At point A, what is the magnetic field created by the wire? Pink wire, yes.
It is mu naught I by pi a, sir.
Mu naught into current is 2I divided by 2 pi into
A.
A. What is the direction of magnetic field?
It's out of the page.
Out of the page. Magnetic field due to the second wire, the green wire.
Mu naught I by 4 pi a, sir.
Inside or outside?
Inside, sir.
Which field is more and which field is less?
B1 is more and B2 is less.
You can find out the net field, adding and subtracting, yes or no?
Yes, sir.
What is the answer for this one?
3 mu naught I by 4 pi a outside, sir.
3 mu naught I by 4 pi a outside. Everyone understands this? Yes or no?
Yes, sir.
At point C, what is the magnetic field B1 due to the pink wire?
Mu naught I by 2 mu naught I by pi a, sir.
Mu naught into current is 2I divided by 2 pi into A by 2. Do we understand this?
Yes, sir.
And the direction is?
Into the page.
Magnetic field to the second wire will be?
Mu naught I by pi a, sir.
Mu naught I by?
Pi a.
2 pi into a by 2. So that will become pi a, and the direction is inside, yes or no?
Yes, sir.
So both of these fields are going to get added up. The final answer would be
3 mu naught I by pi a, sir.
3 mu naught I by pi a. At point D, what is the magnetic field B1 due to the pink wire?
It is mu naught I by 2 pi a, sir.
Mu naught current is 2 pi divided by 2 pi into distance is
2a, sir.
2a. And the direction is inside.
Yes, sir.
B2 will be
Mu naught I by 2 pi a, sir.
and the direction is
Outside.
outside. Both these fields are zero. Both these fields are equal and opposite. Therefore, the magnetic field is going to be zero at point D. Do we understand this?
Yes, sir.
So when the wire carry current in the opposite direction, magnetic field will be zero near the wire which is having smaller current. Do we understand this?
Yes, sir.
If the wire were carrying current in the same direction, then where will the magnetic field be zero?
At point C, sir.
Somewhere in between the two wires. You cannot say whether it's point C or somewhere else. Will it be closer to point to smaller wire, smaller current carrying wire, or larger current carrying wire?
Smaller current carrying wire.
Find the position of point from the wire B where the net magnetic field is zero. So you can just call that point at a distance x from here. So this distance will become 6 minus x. The point will be somewhere in between. Yes or no? Because they carry current in the same direction.
Yes, sir.
Do you understand this?
Yes, sir.
Both the fields should cancel each other out. So magnetic field B due to the first wire, mu naught into 2I divided by 2 pi x, and magnetic field due to the second wire B2 will be equal to mu naught into 5I divided by 2 pi into 6 minus x. I am not looking at the units of thing because everything is going to get cancelled out. Yes or no?
Yes, sir.
You equate the two things and you end up with the answer, and the answer that you will end up would be like this. Do we understand this?
Yes, sir.
These type of questions are coming in the exam these days. I guess in one of your attempts, such question would have also come. So now is the time to do them. This is the next question. What will be the resultant magnetic field at the origin due to 4 infinite wires if each wire produces magnetic field B at the origin? The current is given, X is given, but they are telling you that the magnetic field is B. All the wires are producing the same field. If I look at this wire, let me call it as the pink wire. Pink wire is carrying current in the downward direction. In which direction it will create field?
In the upward direction.
In the upward direction. Let me call this as B. Let me now move on to the third wire, the green wire. The green wire is carrying field in the downward direction at the point O where it will be creating field.
In the positive x direction.
In the positive x direction. Well done. You just have to find out the direction. Now, we look at the blue wire. In which direction is the blue wire going to create field?
Positive y direction.
positive y direction, so it will be B and B will get added up, and the last wire, the yellow wire, in which direction it is going to create field?
Positive x direction.
Positive x direction, so this is 2B and 2B, and the vector addition of 2B and 2B, and the vector addition of 2B and 2B will land you at B root 2B, 2 root 2B. Do we understand this?
Yes, sir.
This is the next question. A wire in the form of a square of side A carries current I. What is the magnetic induction, magnetic field strength, whatever they call it, at the center of the wire? Option C is the correct option. As you can understand that all the wires carry the same current, yes or no?
Yes, sir.
And all the distances are same, so all the fields would be same, yes or no?
Yes, sir.
You just have to understand whether the fields are getting cancelled out or the fields are getting added up, and you will see that the fields are getting added up, yes or no?
Yes, sir.
And all the fields will be pointing in the downward inside direction, yes or no?
Yes, sir.
If you just find out the field due to one wire and multiply it by 4, you get your answer, yes or no?
Yes, sir.
How do you get the net field, B net? 4 times. You just find out the field due to one wire. Field due to one wire is mu naught I by 4 pi. What is the distance of the wire from the center?
A by 2, sir.
A by 2. And if I join their ends, the angle would be 45 and 45, yes or no?
Yes, sir.
2 times sine of 45, so 2 into 1 by root 2. Everyone understands this?
Yes, sir.
You just have to see which option matches it, and I think the option that is matching it is this one, and that is your correct option. Do we understand this, yes or no?
Understood, sir.
Everyone understands this,
Yes, sir.
yes or no? Everyone understands this?
Understood, sir.
I'll give you one more. You have a current carrying wire like this, and you have a point here. All the distances are R. You have to find a magnetic field at the point P. So how are you going to solve this? We look at this wire, the pink wire. We look at this wire, the green wire, and we look at this wire, the blue wire. The pink wire and the blue wire are going to create same magnetic field, same magnitude, yes or no?
Yes, sir.
You just have to see whether they are cancelling each other out or whether they are adding. Cancelling or adding?
Adding, sir.
Adding. What about the green wire? Cancelling or adding?
Adding, sir.
Right. All the wire carry current in the same direction. The wire is point is on the same side. In which direction is the magnetic field going to point of all these 3 wires?
Outside.
It is going to point outside. Let us just find out the magnetic field. Magnetic field B1 will be equal to mu naught I by 4 pi r. If I look at the angles, what are the angles for this one?
1 plus sine 45.
1 plus sine 45. Do we understand this?
Yes,
This angle is 45 and the other angle is 90 degrees. Everyone understands this?
understood, sir.
Magnetic field due to the second wire B2, the green wire, will be equal to mu naught I by 4 pi r. What are the angles for this wire?
2 sine 45.
This is also 45. This is also 45. So 2 into 1 by root 2. All the field are pointing in the outward direction. We have already seen that. Yes or no?
Yes, sir.
Magnetic field due to the third wire is same as the first wire. Yes or no?
Yes, sir.
Mu naught I by 4 pi r into 1 plus 1 by root 2. It is also pointing in the outside direction. All the three fields are getting added up, and that is your answer. Do you understand this?
Yes, sir.
Then this is the next one. You have two current carrying wires I, one carrying current in the outward direction, one carry current inside. You have to find magnetic field at the point P. This theta is given, but the answer is not in terms of theta. The answer is in terms of A and R. So you should get your answer in terms of A, R, and I. So how we are supposed to find out this one? As you can see, magnetic field due to both the wires would be same. Yes or no?
Yes, sir.
Both the wires have the same current. The distances are same. Magnetic field will be same. You just need to see in which direction the magnetic field is pointing. In which direction is the magnetic field pointing? If I look at the pink one, the current is here. The current is outside. The point is like here, here. So if I take the cross product, the magnetic field due to this wire will go like this at an angle of 90 degrees. Do we understand this?
Yes, sir.
Similarly, magnetic field due to the lower wire is like this. Point is here. The magnetic field will go. It should be perpendicular to r vector. So the magnetic field, if I call this wire as the green wire, the magnetic field due to this green wire will go like this. Do we understand this?
Yes, sir.
Both of these fields. Now, you can do it in any ways. You have two vectors, or you can understand this in this way. The vertical components will get cancelled out and the horizontal components will get added up. Yes or no?
Yes, sir.
If this angle is theta, this angle on the other side would be 90 minus theta. So the net magnetic field, B net, will be 2 times B into sine theta. Do we understand this?
Yes, sir.
This B will be equal to mu naught I by 2 pi and the distance is R. Yes or no?
Yes, sir.
The value of the sine theta will be A by R. Yes or no?
Yes, sir.
Which option matches this one?
Option A, sir.
Option A is the correct option. Do we understand how this is done?
Understood, sir.
Everyone got the answer?
Yes, sir.
I'll give you one more on the same scenario so that you can understand the entire concept and become confident in it. So this is the next question that I am getting for you. Two long wires W1 and W2 each carrying current I are placed parallel along the Z axis. The direction of current in W1 is outward and W2 it is inwards. Find the magnetic field at point P and at point Q. Forget about point Q. This point Q is not going to come. So forget about point Q. You just concentrate on point P. Just concentrate on point P. So how are we supposed to do this? If I call this as the green wire, This is the green distance. The distance is 2a, yes or no?
Yes, sir.
And the green magnetic field will be going like this, yes or no?
Yes, sir.
You can easily find out the value of this magnetic field, mu naught I by 2 pi into 2a, yes or no?
Yes, sir.
If I talk about the pink wire, same magnetic field, and it will be going like this, yes or no?
Yes, sir.
Now you have two vectors which are inclined at an angle of 120 degrees. You can do it that way, or you can see that the horizontal components are going to get cancelled out and the vertical components are going to get added up. So the net magnetic field will be like this, yes or no?
Yes, sir.
In this direction, it will be 2b into cos of 60, yes or no?
Yes, sir.
And that is the answer. The answer is B net will be equal to mu naught I by 4 pi a. Are you getting this answer?
Yes, sir.
And the direction is upwards along positive j axis. Everyone gets this?
Yes, sir.
Then we move on. We are done with the straight wires. I'll just give you a formula for magnetic field due to a sheet. If you have a sheet which carries current I and W is the width of this sheet, and you have to find out the magnetic field at point P, what are you going to do is you have to use the technique of integration. You have to break this sheet into infinite wires, and then you have to find out the value of magnetic field. All the magnetic field will be going in the same direction. Just remember this form, mu naught I by 2 pi W. I by W is current per unit length, natural log of A plus W divided by A. That is the answer that you are going to get. So just write it as a note in your books. Okay. Okay. Then you have the next thing, magnetic field due to a loop at the center of the loop. If this loop is a complete circle, the answer is mu naught Ni by 2R. What does this N stand for?
Number of turns.
Number of turns. If the number of turns is 1, it is 1. If the number of turns is more than 1, it will be, you can put the values. Now, instead of a loop, complete loop, if you have a part of a loop, then you can remember the general formula. The general formula of this loop, do you know the general formula of this loop? Mu naught I by 4 pi r multiplied by the angle theta. How much angle theta it subtends at the center? Remember, this theta has to be in radians. Do we understand this?
Yes, sir.
Even this formula is same as this. You see, mu naught I by 4 pi r, the total angle that the circle substance is 2 pi. So the formula is same. Do we understand this?
Yes.
If you have a semicircular wire, what will be the answer then? If you have a semicircular wire, then what will be the answer?
Mu naught I by 4R, sir.
The answer for that one would be mu naught I by 4R. Do we understand this?
Yes, sir.
Yes or no? No, yes.
Understood, sir.
Everyone understands this?
Yes, sir.
This is a small table that you can remember. Let me try to put it. Let me try to put it. Now it's here. In terms of magnetic field at the center, if it is semicircle, it is B naught by 2. If it is 120 degree, it is B naught by 3, and so on, so on. Do we understand this? Yes or no?
Yes, sir.
Now, this is the magnitude of magnetic field. How do you find out the direction of magnetic field? You turn your fingers. If the current is clockwise, it will go inside. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. And then you can note down these simple things. One of these might come in your exam. If the two coils are concentric and carry current in the same direction, fields will get added up. If the two coils are concentric, carrying current in the opposite direction, they will get subtracted. If they are in different planes, the magnetic field will be going like this. Do you know how to find out the direction of the magnetic field? Yes or no?
Yes, sir.
Note it down. I'll give you 2 minutes. Everyone understands this?
Yes, sir.
Then we come to this point where we find out the magnetic field due to a coil on the axis of the coil, and this is the formula. R is the radius of the coil, x is the distance of the coil of the point from the center of the coil, n is the number of turns in the coil. The direction of magnetic field is again given by right hand thumb rule. You turn your fingers in the direction of current, the direction of magnetic field is like this. Whether the point is here, the direction is like this. Even if the point is here, the direction is like this. Even if the point is here, the direction is like this. Even if the point is here, the direction is like this. The direction does not change. Do we understand this?
Yes, sir.
At the center, the magnetic field is maximum. Do we understand this?
Yes, sir.
Now, I had given this formula to the student of 12th standard, and the same question came in one of the attempts. The ratio of magnetic field at the center to the axis. This is the ratio. You can write it in this form. Do we understand this?
Yes, sir.
Then at a distance which is equal to different points, and if you can remember these things, a question came directly from here in this session. So I hope that you can what I have done here is nothing. I've just put some special values so that you can just remember these special values and use them if they come. So these are the results at some special values. If the value of x is plus or minus a, when I say a, it should be plus or minus r. Plus or minus r, the radius of the coil. Do we understand this? The radius of the coil.
Yes, sir.
Okay. So this will be the answer. If sometimes they give you the magnetic field is center 1 by n times the center, what is the value of x? This is the value of x. I think this question came in the exam this days. I don't know. I don't remember it. But something of this nature came in the exam. Do we understand?
Yes, sir.
I will give you everything. Just wait. Then I'll give you time to note it down. You don't have to remember everything. Chalo, then I think it will just get too crowded. You just note this down up till here. Okay? Note down up till here, then I will move ahead. Everyone understands this? Don't have to remember them. I mean, if you can remember them, nothing like it. Everything has been derived from the formula that is given here. We understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Then we can write the magnetic field at very large distance. X is very large compared to R. We will neglect R in terms of X. Do we understand this?
Yes, sir.
If X is very small, we can use binomial expansion. So these are the results. Same results we are obtained from the same formula. Do we understand this?
Yes, sir.
This is the graph of B with R. And as you can see at the center, the B is maximum. Do we understand this?
Yes, sir.
And the value is mu naught I by 2R. Yes or no?
Yes, sir.
There are 2 points which are known as points of inflection. At this point, the rate of change of dB by dx is 0. These are known as point of inflection where the curve changes its shape. On one side of that thing, it is having positive slope, on the other side it is having negative slope, sort of thing. Do we understand this? It changes its shape.
Yes, sir.
These are known as points of inflection, and this points of inflection happens at r is equal to plus x is equal to plus r by 2 and minus r by 2, both sides, and the value of magnetic field is mu naught ni by r into 4 by 5 root 5. So just note these things down. Do you understand this?
Yes, sir.
Now this arrangement of coils, and I've seen questions on this, is known as the Helmholtz coil arrangement, and this arrangement is used to manufacture uniform magnetic field for a very short range. So basically it consists of two identical coils on the same axis, same current, same number of turns, same radius. The distance between the center of the two coils is equal to the radius. They carry current in the same direction. The planes are parallel to each other. The current is same. Then this combination is known as the Helmholtz coil arrangement, and you can see between these 2 points the magnetic field is almost constant. Because of the superposition of these two, the magnetic field is almost constant, and the value of this magnetic field is almost equal to the magnetic field at the center, which is equal to that value that I had given multiplied by 2. So it becomes 8 by 5 root 5 mu naught ni by r. Do we understand this?
Yes, sir.
So this arrangement is known as the Helmholtz coil, and in this Helmholtz coil you will see there are 3 points of inflection, A dash and A double dash, and that is what you need to remember. I've seen one question coming on this Helmholtz coil, and that is the reason I have given you this. You don't know what can come, and if one thing comes and you don't know about it, it's straight away -5. So you can write this, what is Helmholtz coil and what is the purpose and what is the magnetic field. Then you can move ahead and write this. In some cases, the magnetic field at the center of the arrangement is going to be 0. These are the cases that we have drawn. See, if a current I comes from here, the current will get divided. We have seen the question where we have found out the current getting divided. That's all no.
Yes.
Now, if the portions are equal, current will be equal. Both the currents are in the opposite direction, so they will create equal magnetic fields. Everything will get cancelled out, so magnetic field at the center would be 0. Do we understand this? The first case is very simple to understand. Yes or no?
Yes, sir.
In the second case, what will happen is the current which grows in this branch and current which grows in this branch will be unequal. Yes or no?
Yes, sir.
Which branch will get more current and which branch will get less current?
I2 will get more current and I1 will be less.
I2 will get more current because the resistance is less, and I1 will get less current because the resistance is more, but their resistance are in the ratio of their lengths. Yes or no?
Yes, sir.
And their lengths are in the ratio of their angles. Yes or no?
Yes, sir.
But I1 current is smaller, but the angle is more. I2 current is more, but the angle is small. Magnetic field also depends on the angle. So again, what will happen? The angle ratio will again get cancel each other out. And in this case also, the magnetic field will be 0. Do we understand this?
Yes, sir.
So in this case, magnetic field is 0. In this case, magnetic field is 0. Similarly here, this current I1 will be more, but this current I2 will be less. Again, their ratio will be in the ratio of their lengths. But again, the magnetic field will for the upper portion magnetic field will be 2 times, for the lower portion magnetic field will only be 1 time. So again the magnetic field will get cancel each other out, and on all these cases the magnetic field at the center of this symmetrical figure would be 0. Do we understand this?
Yes, sir.
So these are the different cases. If a question comes, directly just mark 0, because you understand the logic and concept behind this. I will give you 2 minutes, note it down, let me know once you are done. So you have noted down all these points, yes or no?
Yes, sir.
I'll give you time so that you can recollect these points. At the same time, I've sent you a sheet which has all these questions given in the form of a sheet. Do you remember that sheet?
Yes, sir.
So what I will suggest you is you can try questions from that sheet and see how many questions you can do. I will also take some questions from that sheet. Do you know which sheet I'm talking about?
Yes, sir.
Which sheet?
Mm, sir, that current you have given.
This sheet I'm talking about. This sheet. Do we see this sheet?
We
You
didn't
see
got.
this sheet?
Ochina.
You see this sheet? I've sent you this magnetic field ka sheet. So try questions from this sheet, okay?
Okay, sir.
All these questions, all of these question can come, and some of these question have come in the exam this year. So try questions from this sheet. I will take some questions from this sheet in the next class. If you're done with this sheet, that means the magnetic field is done. The next class we will complete this sheet, and we will also complete the next part of this chapter, which is Ampere's law. So I'll see you there. Everyone understood what we have discussed in today's class?
Yes, sir.
Okay, then I'll see you tomorrow. Take care. God bless you. Bye bye.